the previous video, we left off by examining the conditions of each of the reactants right before the chemical reaction started. So naturally, that is where we're going to pick up in this video at the point where our two reactants OH- and CH4Br actually get close enough together so that they collide, thus beginning the chemical reaction. Now, in terms of visualizing what happens to kinetic energy and potential energy, it's best to make an analogy to think of each of our reactants as literal moving vehicles. If there are two cars that are moving in opposite directions towards each other at the same speed, at the moment when they hit each other, their speed is going to be zero because the speed of one vehicle hitting the other vehicle and canceling out its speed results in both of them stopping at the moment of collision. Now, this is an oversimplification, even though the two particles are moving, in this case, towards each other. There's no guarantee that they're moving towards each other at exactly the opposite directions and exactly the same speeds. So there's no guarantee that their kinetic energy will completely cancel each other out because nothing at the atomic level ever stops moving. But we can say that because they are moving in at least partly opposite directions, that some of their kinetic energy is going to be canceled out at the moment when they hit each other, which means that we can say that the kinetic energy in this reaction is at its lowest point in the reaction at the moment of the collision between our two reactants. Now, we know from the law of conservation of energy that kinetic energy can neither be created nor destroyed, and we know from our thermal energy equation that if kinetic energy decreases, then potential energy must increase. Therefore, the energy that is lost as kinetic energy must be converted into potential energy, and we know that most compounds store their potential energy in their bonds, which is why this structure here has the rather unusual structure of having a central carbon that has 5 bonds. This structure is obviously not stable because, as we know, carbon cannot actually make 5 bonds because it doesn't exist on energy level 3, which means it can't make an expanded valence shell. Now, the only way for us to resolve this structure is for one of these two bonds here to break. Now, which one breaks depends on whether the reaction is successful or not. This structure here, this very unstable and very temporary structure that usually contains a central atom with more bonds than is possible to make, is what we call an activated complex. Activated complexes form in the middle of a chemical reaction at the point where the potential energy of the reaction reaches its highest point, which corresponds with the kinetic energy being at its lowest point due to the collision. Activated complexes, in short, are a combination of all chemical reactants within the reaction itself hitting each other and resulting in a temporarily highly unstable structure where one of the bonds that is newly formed is going to break. And that's exactly what we see subsequently. So when the OH- collides with CH3Br, one of the two bonds breaks, and if we assume that our reaction is successful, that would mean that the Br has broken off, that its bond turned into a lone pair. Now, if the activated complex has broken a bond, and bonds are the principal location where potential energy is stored, that means that the potential energy of this compound is going to decrease. And that means that this stage, the breaking of the activated complex, corresponds to this section here with a decrease in potential energy. However, we know energy can neither be created nor destroyed, which means that this potential energy must go and become kinetic energy. Now, if kinetic energy is going to increase, that logically means that these two particles, which eventually are going to be our products, are going to move faster than what they were moving before. Therefore, if our two products are moving faster, they're not going to stay together, they're going to move apart. The simple reason for this is if we look at charge, our bromine, which is now an ion, has an extra pair of electrons, which means its negative charge is even stronger than before. Now, considering all of the electrons that exist in all of the bonds of our newly formed product molecule, based on all of these electrons here, this negative charge doesn't want to stay next to the other product, and therefore our products are not going to stay together, but instead are going to move away from each other. And if they move away from each other, they cannot react with each other. So if the products no longer can react, that means, assuming the temperature is constant, that our potential energy stays constant because we're not breaking or reforming bonds. And assuming the temperature remains constant in this reaction, our kinetic energy is going to stay constant as well, and our reaction has now finished. So as a summary of the general progress of the reaction, remember about all of the different measurements that we can see on a potential energy curve. We know that the difference between potential energy of the products and the potential energy of the reactants occurs here. This is our delta H value. But now that we know that the activation energy is the energy that's required to make this reaction occur, we can conclude that the activation energy, E sub A, is this distance here. What this means, given that activation energy is the difference in potential energy between the unstable activated complex and the potential energy of our reactants, we can make a further clarification to what activation energy is. So activation energy is the energy required for the reactants in a chemical reaction to form the activated complex. Because once the activated complex is formed, this structure is so unstable that the rest of the reaction will happen by itself as long as this bond here breaks and this bond here is formed successfully. And therefore, as long as we can make the activated complex, the reaction is pretty much guaranteed to happen. Hence this definition of activation energy. In the final video in this topic, we will examine the relationship between the activation energy and delta H, kinetic energy, and forward and reverse reaction directions in order to basically summarize everything related to potential energy.